Good afternoon. I'm going to be presenting to you the modeling and simulation of a high-rise elevator system to predict the dynamic behavior of, to predict the dynamic interactions between its components. This presentation is part of my PhD research, which is co-sponsored by the University of Northampton and the ThyssenKrupp elevators. The scope of the presentation will be introduction, description of the vibration model, case study, and results and conclusions. As introduction, all high-rise buildings vibrate due to wind. This, as you can see in the picture, the wind, when it impacts the high-rise building, it causes turbulence at the other side. The displacements at the top of the building will depend majorly on the speed of the wind, the building height, the robustness of the structural design, and if the structure has an active mass damper or a mass damping system. Elevator ropes vibrate at very low frequency, and the high-rise buildings also vibrate at low frequency. When both frequencies matches, it causes resonance. This resonance phenomena appears and causes also high amplitudes in the elevator ropes, which eventually will impact the elevator shaft, causing noise to the people that reside in the building, and also will cause damage to the elevator components. In these two pictures, in here we can see the orbit tower located in London at the Olympic Park. This structure is a steel structure which is very light, and it is in a prone area, located in a very prone area of winds, and also has an active mass damper. This structure causes resonance also to the elevator ropes. And at the other side, we have Burj Khalifa, which is located in Dubai, which it has a height of 800 meters approximately. The orbit tower has an approximate height of 100 meters. Both structures causes resonance to the elevator ropes. The description of the vibration model will be consisting of the traction sheave, diverter pulley, elevator car, compensating sheave, counterweight, and will be connected to through suspension ropes and compensating ropes. The ropes will be vibrating in the lateral in plane and lateral out of plane direction, which are represented by the letter V and W. The car, compensating sheave, and the counterweight will be restricted its movement only in the longitudinal direction, which will be represented by the letter U. The excitation to the system will correspond at the top of the traction sheave, which will be excited in the lateral in plane and the lateral out of plane direction. When the display epsilon is the displacement of each mass corresponding to the building motion. The vibration model. The vibration model begins by describing the tensions in each ropes. The tension at the suspension ropes, at the car side, it is represented by this equation. The tension but the compensating ropes at the car side, it is represented by this equation. The the tension at the compensating rope at the counterweight side, it is represented by this equation. And at the tension at the suspension rope at the counterweight side, it is represented by this equation. After applying the Hamilton principle, we obtain the equations of motion for the ropes, which are represented in the three directions. The subscripts t and x represent the partial derivatives with respect to t and x, and epsilon represents the actual green strain of each rope. We also obtain through Hamilton principle the equations for the masses, which are for the car, compensating sheave, and counterweight. Also, through the Hamilton principle, we obtain the boundary conditions for each rope. For example, in this case, I will be showing you the boundary conditions for the suspension rope at the car side, at the beginning and at the end. And the actual green strain, it is represented by this equation, which contains the longitudinal, lateral, and lateral in plane and the lateral out of plane directions. In the lateral in plane and in the lateral out of plane, displacements of the ropes can be expressed with the following two equations. The lateral in plane, the V and W with the dash, are the displacements of the rope relative to the configuration of the rope when it is stretched by the building motion. And the other two components represent the rope stretch due to the deformation of the building. And the deformations of the building can be obtained with the following shape function, which is the equation for a cantilever beam. To solve the equations obtained from the Hamilton principle, which are nonlinear partial differential equations, we use the Galerkin method with the following shape function, which we obtain at the end nonlinear ordinary differential equations. We use the sine function because it satisfies the boundary conditions from the Hamilton principle. After integration from the Hamilton principle and applying the equations for the lateral in plane and the lateral out of plane, we obtain the following two equations for the lateral in plane and the lateral out of plane direction of each rope. The zeta in each equation represents the modal damping for the rope, for each rope, and the omega represents the natural frequency of each mode of rope. The k with the dash represents the coefficients of the stiffness, the coefficients from the stiffness matrix, and the f with the dash represents the coefficient from the force vector, and the n represents the nonlinear terms from the representing nonlinear coupling. In here, we can we can emphasize in two clear examples where this mathematical model the stiffness incorporates the displacements of each mass. For example, the stiffness for one term has the displacement of the compensating sheave and the displacement of the car. This is a secondary excitation of the system, which it is called which is called autoparametric terms. Another type of excitation is the nonlinear terms, which for the ropes have the lateral in-plane and lateral out-of-plane displacements for each rope. In the equations of the ropes, these terms are cubic, and for the masses, they are quadratic. After applying the Hamilton principle and using the Galerkin method, we obtain also the equations of the masses, which we transformed into its modal coordinates. The zeta represents also the modal damping of each mass, and the omega represents the natural frequency of each mass. The y vector with the superscript 1, 2, and 3 represents the mass modal. Represents the mass modal vector. Represents the mass normalized mode shape matrix. Are the coefficients from the mass normalized mode shape matrix. In this presentation, I'm gonna show you the force vector, the excitation vector, the excitation term for the car, which has the excitation of the system in the lateral in-plane and in the lateral out-of-plane. Also, the nonlinear terms for the lateral for the car also contains the lateral in-plane and in the lateral out-of-plane displacements for the suspension rope and for the compensating rope at the car side. Okay, the case study. The case study will correspond to an elevator which will be positioned at the top landing level, and will have the following. We'll have these parameters. The model will be excited at the top in the lateral in-plane with an excitation of 0.19 Hertz and a displacement of 7 centimeters. And in the lateral out-of-plane will be excited with an excitation of 0.05 Hertz and a displacement of 5 millimeters. As a preliminary results, we obtain from the free vibration analysis, we obtain the natural frequencies of the ropes. And we can see that the compensating ropes at the car side have 0.19 Hertz. So this means that we are going to be exciting the mathematical model to obtain the resonance in the compensating ropes. Also, this is almost the longest rope in the system, and also has the less tension at the rope. Also, from the free vibration analysis, we obtain the vertical natural frequencies of the system, which are these ones. In this plot, I am showing the variation of frequency with the position of the car for the compensating rope at the car side. The four curves are the frequencies, the first, second, third, and fourth frequency of the rope, and the horizontal lines are the are the frequencies in which the building it is being excited. The car is positioned at this level, at the highest level. This plot represents the lateral out of plane and the lateral in plane in time, and has this type of shape. In this plot, it is the superposition of the time and has this type of shape. In this slide, I'm showing the displacements in the lateral in plane and the displacements in the lateral out of plane. In here, we can see that the energy is being dissipated of the system from the lateral in plane to the lateral out of plane, and the amplitude of the rope in this around 150 seconds, it starts increasing, and this is a cause of the whirling motion of the rope. Determining the FFT or the frequency in a time sample between 235 and 274 seconds for the lateral in plane, we see that the frequency it is 0.19 hertz, which is the same as the frequency we are giving in the lateral in plane. And for the lateral out of plane, we have that in the same time sample, the rope it is experiencing two types of frequencies, but the predominant frequency is the 0.19 hertz and has the 0.05 hertz that we are exciting the system. For an animation that I did in MATLAB, it is a 3D animation of the complete system. Where we can see that the compensating rope it is being excited and causes the resonance in the system. Continuing on, as the conclusions, this model can be used to capture a range of resonance in the system which are caused by the building motion. One phenomenon that involves the transfer of vibration from the lateral in plane to the lateral out of plane direction. The third conclusion is that the transfer of energy from the lateral in plane mode to the lateral out of plane mode takes place through the autoparametric terms. And as a fourth conclusion, that another phenomena which is being investigated is the excitation of the car compensating sheave and the counterweight through the vibration of the ropes. Thank you for your attention.